It's a great pleasure to welcome all of you to today's Wrigley lecture series. As you know, the series is named after Julian Wrigley, whose generous support enabled ASU to establish its presence in the domain of sustainability and future thinking. And that was manifested early on by the foundation of the Global Institute of Sustainability, now the Global Institute of Sustainability and Innovation in 2004, the School of Sustainability in 2006, and then ultimately the Global Futures Lab named after Julian Wrigley in 2019. So I'm really thrilled to recommence this series, which was last held during COVID virtually in about spring of 2020. The Wrigley lecture series, of course, brings together thinkers and problem solvers to our community at large here at ASU to have a dialogue about sustainability challenges and opportunities to help us envision a future in which all life can thrive on a healthy planet. So each guest speaker is selected based on the timeliness and groundbreaking nature of their work, following recommendations by either Global Future scientists, and we have more than 800 Global Future scientists at that point, graduate and undergraduate students, or staff of the Global Futures Laboratory. Today's talk will be given by Mark New, who is the founding director of the African Climate and Development Initiative at the University of Cape Town in South Africa. I'm not sure how many of you had a chance to visit Cape Town, but if you haven't and you have a chance to go there, I just told Mark, to me, often coming out of the ice towards Cape Town, to me it was always like paradise. It's absolutely beautiful to see Cape Town in front of the Table Mountain and then go through the town and see all the beauty of it. So Mark actually got his master's in environment and development and his PhD in geography with specialization in hydroclimatology from the University of Cambridge. His PhD thesis focused on climate change impacts on water resources in Southwest Cape, South Africa. So many of you will see the parallels to some of the issues we are working on and we are confronted with. His research has encompassed the development of global climate datasets, detection of climate change trends, climate modeling and scenarios, assessment of uncertainty in climate projections and impacts, attribution of climate change impacts, and climate change adaptation. So you can see you will be treated by quite a broad range of thought about climate and its impact. For his work, among other recognition, he was recently awarded the 2023 Frontiers Planet Prize. He's currently on sabbatical as a Fulbright visiting scholar at the University of California's Santa Barbara Brent School of Environmental Science and Management. He's joining us today to discuss work on impact attribution using examples from water security, food security, and sovereign catastrophe insurance. So given the summer we just experienced, this is really a most timely topic. Just to remind some of you who are not following the news as much as others, globally August 23 was the hottest August to date, and not just by a little bit, but by a good solid margin. There is almost no chance, in my view, that we will not record the hottest year on record this year, especially given the El Niño conditions in the Pacific. We also experienced, or witnessed actually, not experienced, Hawaii, the wildfire in Maui, Hawaii, which reminded us a bit of the Australian inferno that we witnessed in 2020. And last month, in eastern Libya, Storm Daniel passed through the region, bringing heavy rainfall and flooding that resulted in large-scale destruction, which now actually is considered the deadliest Mediterranean tropical-like cyclone in recorded history, with winds reaching 70 to 80 miles per hour, which for this region is really high. So what that means is, and we will see more, I think, in Mark's talk, we are actually seeing more extremes of different types in more areas, higher frequency and higher amplitude. That's the world we are moving into. But then climate change is not the only challenge we are confronted with. And given the present crisis in the Middle East, Gaza and Israel, in essence another war besides the one between Russia and Ukraine, I just want to make sure that we keep in mind when we are talking one aspect such as climate, that we are actually in a world that has multiple pressures, a lot of them on the social or societal side. And that is clearly something, these simultaneous occurrences of social instability and extreme weather events, they compound the pressure that our planet already is under. And this is why we have the Wrigley lecture, to really contemplate these kind of events, how they hang together, what they mean for us, and what we can do to minimize the occurrence and the impact of them as we are going into the future and as we are thinking about the viability of our planet. So with that, and without further ado, please join me in welcoming Mark New to deliver his lecture with the title of Using Climate Impacts Attribution to Inform Adaptation Action.
Thanks very much for that introduction. I will start off and get going. So I think I changed my title a little bit, and it's not your fault, but it's more to inform climate risk action or risk reduction action, but it's basically the same as adaptation. So I'm going to talk about some strands of work that I've been sort of leading over the last 4 to 5 years in the area of climate change attribution. But what we've been really trying to push, as you'll see in some of the results that I show, a shift from just thinking about the climate system to thinking about the receiving environment that climate extremes occur in. Because we know that often one of the main channels that climate risk or climate hazards, or one of the main ways that climate risk propagates through is through hazards and extreme events. And then actually what matters is not so much whether Hurricane X was 3 times more intense than before, but actually what it meant on the ground in terms of both environmental, social, and economic damage. So we're trying to move some of this climate change attribution work into looking at impact attribution and trying to disentangle different contributing factors to the on-the-ground impacts of extreme weather and climate events. So perhaps I should just start, for some of you who may not be as deeply embedded in climate change attribution world as I am. What is climate change attribution? It kind of started out in the 1990s with the first IPCC reports, and at that stage it was largely around trying to understand whether global trends observed in temperature were actually due to human influence on the climate or natural variability in the climate, or some combination of that. And sort of classical climate change attribution is a 2-stage process. One is detecting a change in the system that you're interested in. So in 1990s, it would have been global mean surface temperature. Is that a statistically significant trend that you can say with confidence that there's something happening that you wouldn't expect through interannual or multi-decadal variability? And then if you can detect a change or a trend, then assessing different hypothesized factors that you think might be causing that trend to disentangle what the real underlying causes are. So in terms of global mean temperature, obviously the main culprits are greenhouse gases, but we have the confounding effects of aerosols, which act to offset that. We have solar variability on interannual, decadal, and multi-decadal timescales. And then we have some weird hypothesized possible causes like variations in cosmic ray incidence, which is supposed to change cloud condensation nuclei and have a feedback effect on planetary albedo through creating more clouds at particular times of the year. So the attribution work would be trying to disentangle which of these causes or which combination of causes would be most would be the ones that seem to be the most likely culprits, if you like. So as I said, in the 1990s, the work was largely on large-scale trends in temperature, some emerging work on regional temperature. As we moved into the 2000s, again at large scale, there was work to start to do attribution on trends in other variables like ocean heat content, regional rainfall trends, trends in river runoff, etc. And then a first dig into individual extreme events. And the first study that looked at that was a study on one of the European heat waves that was able to attribute a human influence on the intensity of that heat wave. And then in the last couple of decades, we've moved more and more into the extreme weather and climate event world, looking at rainfall, cyclones. You people in this part of the country will know all about fire risk and attributing fire weather conditions and whether those have changed as a function of human influence on climate. And then towards the end of the last decade, of the 2010s, starting to get into impacts. So can we make attribution statements around impacts? I think the 2020s, going forward, we're really in this area of looking at more on-the-ground impacts. So both what we call operational event attribution, which is having a capability to immediately after an event like the Libya flooding, to be able to actually come up with a statement while it's still in the news about what the human influence is there, rather than spending a year working on it in our labs and then coming out with a statement later on. And then the socioeconomic impact. So what do these extreme events mean on the ground? And what we've been working on over the last 4 or 5 years are some of these. So both the meteorological aspects of these events, but also trying to move into the environmental, social, and economic impacts. So I'm going to be largely talking about what we call event attribution. So that's when you have an extreme event, we're interested in whether we can detect a human influence on that event. The traditional form of attribution is more around detecting a trend and seeing whether there's a human influence on that underlying trend. So we're looking at individual events, and I want to just give kind of a 101 on how we go about doing that. And a nice analogy is to think about medical attribution or epidemiological studies, right? We compare two samples, they're with and without an hypothesized cause or characteristic we're interested in, the factual versus a counterfactual. So an example from medicine might be people who smoke and people who don't smoke, right? So you've got a nice sample of, and then you can look at the likelihood of a particular medical outcome, whether it's lung cancer or something else. And what we know is that people who smoke have a higher likelihood of getting lung cancer. And from there, you can work out the probability in that population. So your probability of those who smoke is different to the probability of getting cancer to those who don't, and you can get a risk ratio. So what's your attributable risk from smoking in terms of increased likelihood of cancer? So that's the kind of the framework that we use in event attribution. So instead of people who smoke, we've got like a world that smokes, if you want to think of it that way, a world with greenhouse gases and a world without greenhouse gases, the likelihood of a particular climate phenomenon or trend that we're interested in, and we can compare those likelihoods to get a risk ratio for a particular type of event of a given magnitude that we're interested in. And then we say we've got an attributable human influence if that risk ratio is statistically greater than 1. So we use a very probabilistic approach to this so we can get confidence intervals for that attributable risk, and from there we can start to make attribution statements. Okay, so our challenge is that we only have one world. So unlike in medicine where you've got hundreds of individuals or populations or groups of people, we don't have a counterfactual of a world with no climate change. So we have to use climate models and statistical models to simulate these counterfactual worlds. And that's where we head into the, if you like, the computer laboratory to represent the climate system with and without human influence on climate. So there are three main ways that currently attribution science goes about trying to do this. The first is using statistical models. And here we would say we have a time series of monthly maximum temperature, and we're interested in extreme temperatures. We can fit an extreme value distribution to that. And the critical thing is that we will have a covariate that's part of that statistical model, that fitting process. Usually global mean temperature, or perhaps regional temperature. And then, given that, the shape of that extreme value, and therefore the estimated magnitude likelihood relationships for that variable of interest, will vary as a function of global mean temperature. And we can estimate what the return period of a temperature event of a given magnitude would have been back in, say, 1850, when we adjust that temperature covariate back to a pre-industrial temperature. So here's an example of some work related to the case study I'm going to give later, which is the Cape Town drought. You've got two long curves there, a return period versus magnitude on the y-axis, and the blue curve is the estimated sort of return period curve for a pre-industrial climate using this method, and you can see that that's significantly different from the red curve. So the likelihood of drought of the kind of magnitude we experienced would have been significantly lower. It would have been a less frequent event, a higher return period in a world without climate change. The second approach is using coupled ocean-atmosphere climate models. We make use of the IPCC-type climate simulations, where climate models are run from pre-industrial radiative forcing greenhouse gases through into the future. But we also make use of a parallel set of simulations that essentially just run the same time period, but with pre-industrial concentration. So we don't ramp up the forcing over time. We just keep the natural forcing in there, so solar radiation and observed explosive volcanic eruptions. And then from there, we can estimate return periods for the variable of interest from these two families of simulations with and without human influence. A challenge with these types of approaches is that, for those of you who know climate modeling, you initialize a climate model in 1850, it starts running along, and it basically becomes deterministic chaos, means that it basically diverges from the real world very, very rapidly, and they just have their own sort of characteristic variability. So an El Nino event, for instance, in one of those simulations will not necessarily occur at the same time as an El Nino event in the real world. So we have to essentially capture statistics of the variable of interest, but we can't tie it to a particular date. And the other problem is that related to that, because we're not looking at a specific event, we're looking at a family or type of events, we can't capture the dynamics of a specific event. So we can't look at some of the dynamical underpinnings of an extreme event we're interested in. So the third approach is I just wanted to show an example, of the types of results one gets. This is for global mean temperature, but it's quite a familiar diagram. But the blue curve at the bottom is the simulated global mean temperature from 1850 to roughly the present, with only natural forcings. And then you'll see that the sort of orangey-brown curve is with all forcings, including greenhouse gases and aerosols. And that tracks that black curve much more regularly, which is the observed global mean temperature record. So here this is the kind of work that enables the IPCC to say it's unequivocal that human influence on climate has caused the observed temperature change over the last 50 years. So we use these same model results, but are looking at individual, localized measures of a local climate variable, but it's the same modeling experiment. The third and final method is to use what we call atmospheric models. So these are like weather forecast models. So they only simulate the atmosphere, but we can force them with the observed land surface and ocean sea surface temperature conditions, sea ice conditions, and you actually run them almost like a weather forecast. So the same way a weather forecast would assimilate data at the start of the forecast period and simulate the evolution of weather and of the weather over the 10 days, these kind of atmospheric models do the same thing. So you're capturing the ocean forcing of weather at the time that this event happened, and then we run a counterfactual by removing the estimated global warming signal in sea ice in ocean temperatures. So we still have the spatial patterns of sea surface temperatures or soil moisture over land, but just with the climate change signal removed. And then essentially we just have these two so-called weather forecasts of this event in a world with and without the human influence on climate. And again, here's another example from the Cape Town drought. We just need to look at the blue and the red curves. That's 3-year rainfall deficit and a likelihood magnitude relationship. And you can see that the blue curve sits above the red curve, showing that in this case a human influence has been detected on the severity of a rainfall deficit in this particular instance. So that's kind of the background. Sorry about all that, but I think it'll help understand some of the work that I'm now going to talk about in terms of examples of the kind of research that we've been doing. So we're interested in impacts attribution. So that's going from the weather and climate attribution through into what that means on the ground. And here we have to go one or a few steps further, because we have to propagate those climate change data from the factual and the counterfactual climate worlds through into impacts on the ground. And to do that, we need a well-evaluated model of the impacted system, whether it's, say, a hydrological system, I don't know, the GDP of a country, health impacts, mortality, heat mortality relationships, whatever. So we have to find these models that have been tested and proven to be reliable, and then we can essentially join them up by feeding the weather information through into those models to see how does that propagate through into an impact on the ground in that modeling framework. So one of the first studies that did this came out in 2016 by Dan Mitchell and co. And they looked at one of the more recent heat waves in Europe and had a heat mortality model that had been well established and validated in Paris and in London. And they could show that when you ran the climate model simulations through the heat mortality model, they ended up with a detectable and attributable influence on the level of mortality during that event. So the red curve is what was observed, and the blue curve is the counterfactual. And you can see that those two likelihood return period death magnitude curves are separate from each other, so they would therefore have this detectable and attributable influence. So we're essentially we've been trying to take this work forward in a number of different areas to look at this kind of impacts attribution work. So the first example I want to talk to you about is the Cape Town drought, the famous, at least in South Africa, Day Zero drought, which occurred in 2017-18, but was actually the result of a cumulative series of 3 dry years in succession. The crisis only happened in the 3rd year, but it was a sort of a cumulative drought. And in this work, we asked a number of different questions. So first, was there human influence on the meteorological drought? So on the rainfall deficit, that's kind of classic extreme event weather attribution. Was there human influence on the hydrological drought? So how did that meteorological rainfall deficit propagate through into river flows that went into the reservoir systems? And then the third question was actually, was there human influence on the receiving environment? Because one of the challenges you have is that you can exacerbate the severity of an impact depending on how well adapted you are on the ground. And in our case, we have a serious problem of invasive alien vegetation in our watersheds that use much more water than the natural vegetation and can actually act to really, on their own, reduce river flows. So we were interested in how the states of the catchments themselves actually acted to either exacerbate or ameliorate the climate signal in the hydrology. So a bit more on the Cape Town drought. As I said, there were 3 successive dry years, and the top graph there shows the cumulative level of all of the major reservoirs that supply the Cape Town and other areas with water. So in 2014, at the end of the rainy season, the reservoirs were full, the reservoir system was full, and then 2015, 2016, and 2017, 3 dry years in a row, you can see that the maximum reservoir levels slowly declined. So in 2017, they were at about 40% of capacity at the end of that 3rd dry, below average winter rainfall period. And then the red bars, the red sort of panels, are successively intense water restrictions that were being imposed by the city in anticipation of this. And effectively what happened was that in the first year of the drought, there was very little, the water restrictions were quite light and behavior didn't change. But then in the 3rd year of the drought, when this messaging around day zero being the day when we can't extract any more water from our reservoirs, then there was a massive behavioral response. And that's the bottom graph, which is showing the city of Cape Town's water usage over those same cycles. So you can see that water usage goes up in the summer and the dry season, out of sequence with the rainy season. But then in that final year of 2017, the actual water usage in the city dropped by nearly 50%. And it was a combination of that huge behavioral change and demand reduction, along with some emergency augmentation, and a very fortuitous water transfer for one of the big agricultural areas where they suddenly discovered they had extra water that they didn't need, that actually saved Cape Town from running out of water before the next rainy season arrived. So that's kind of the background, and I mean, there's been a lot of work done on all different aspects of this drought. But our work, or this work I'm going to talk about now, is more around the attribution side of things, the physical, natural dimensions of the drought. So the first question was there a human influence on the meteorological drought? And what we really wanted to test was whether this drought, here's the 3-year average deficit of rainfall over the region that supplies Cape Town with water, and it was a really, really dry 3-year period. So we wanted to say, was that red pattern there, that red and orange pattern, was that just natural variability, or could we find a human influence on the severity of the drought? And using this attribution method, using multiple different models, and I won't go into the details here, but we had the observational method where we use the statistical modeling. We had the CMIP, the coupled models, and we had a set of atmospheric models. You could come up with an estimate of what that risk ratio was. So how much had the risk of an event of this magnitude been increased? And you'll see across all of those panels, the black bar being our best estimate of the risk ratio, they're all sitting in the range of 2 to 5, so a 2 to a 5-fold increase in the likelihood of a drought of that magnitude. When you put it all together into that purple bar, which is kind of our synthesis, then you get a risk ratio, an estimated risk ratio of 3.32. So a 3-fold increase in the likelihood of a drought of this magnitude due to human influence on climate. We've also looked at the synoptic conditions that led to that drought, because obviously we were looking there at rainfall on the ground, but we need to it's also nice to understand the mechanisms through which that drought manifests itself. And we're in a Mediterranean climate. I won't go into a lot of detail here, but we have so all of the rainfall comes through mid-latitude rainfall systems, the westerly rain belt, and you have certain circulation conditions that essentially force the waves, the Rossby waves, to either peak to the east or to the west of the country, and the storm tracks miss the country, or to be depressed further south, and they never hit southern Africa, or to actually be pushed into the Cape region. And so each of these different circulation types has different likelihoods of rain-bearing systems hitting the Cape, and we could detect during this drought period, and actually a long-term trend as well in the frequency of rainfall-bearing circulation conditions. And so we were able to show that the main mechanism through which we had this drought occurred was actually through changes in circulation, combined with a little bit of a change in the amount of water that was in these systems when they were coming through and dropping rainfall. So we're having fewer rainfall systems, and those that did come had less moisture in them because of the change in the thermal gradient as we go from the subtropics into the intertropics. So we then also, moving on to the hydrological drought, this is where we were really trying to look at how those meteorological conditions fed through into the catchment hydrology and the catchment state. There were sort of two questions here, as I said at the beginning. So did climate change, anthropogenic climate change, as ACC in this diagram, impact on the drought period stream flow? And then secondly, can management of these alien invasive trees actually modulate this impact? So this is one of our catchments that we studied. That catchment should not look like that. It shouldn't look like miniature redwood forests from the coast ranges of California. It should look something like that, which is with a more of a chaparral type shrubland vegetation that is really well adapted, doesn't use a lot of water. Instead, it's invaded with a whole lot of, mostly with pines, but also other escaped forest species, including acacia, and the water use from these invaded so the evapotranspiration from these invaded catchments is incredibly high compared to the natural vegetation. So that immediately then means there's less water infiltrating into the system to feed and replenish the rivers. So we were interested in understanding both the interaction of these climate forcings, if you like, on the hydrology, where we did the standard attribution work of having modeling the impacts of the meteorological drought on the hydrological system with and without climate change, but then also what that meant under different land cover conditions. And we had 3 different land cover conditions. So we had the current state in several of these catchments, and that's the top diagram there that shows the current catchment. The red area is the currently invaded area. The green area is the area that's under natural vegetation. And then we ran a detailed hydrological model under different land cover conditions, essentially. The current situation, if restoration was not implemented and the invasion continued to full invasion, and if we had actually had very successful restoration and the whole catchment was green and we had almost like a pristine catchment. So a heck of a lot of work in getting to this stage, and it's always a bit embarrassing when you show your results and it's one kind of graph, but that's what I'm going to do. So here's all of that work, and you get kind of one graph like this. But essentially what we're showing here is something like that risk ratio. So it's the percent reduction in river flows during the drought period that can be attributed to different things. And the interesting thing is we've got 2 catchments here. One on your left, the Berg catchment, which was only lightly invaded, 9% invaded. That's the diagram that I showed you. And then one of the other catchments was quite heavily invaded, had a 40% level of invasion. So nearly half the catchment was covered with alien vegetation. So when you have the sort of current level of, so the top is the combined impacts of anthropogenic climate change on the current state of the catchment. And you can see that the climate change reduced the dry season flows with the catchment in the current state by between about 15 to 20% roughly. Okay. When you then work with sort of totally clearing those catchments, you can see that the reduction is reduced. So particularly in the heavily invaded catchment, you've got almost a halving of the severity of the hydrological drought. And if you allow the catchment to go to full invasion, which is the brown bars, then you can see that you're really you can really exacerbate the impact of the drought. So river flows reduced by 30 to 40%. So what this results showed that there are positive results from actually keeping the receiving environment in a well-adapted condition, and we can actually quantify what that means in terms of water yield and put a value onto that, so you can actually come up with a financial model for what the return on investment in catchment restoration might be. And we could show that you could actually, I'm not showing this, but with financial modeling we could show that over a 20-year period, if you invested for 20 years in clearing and then maintenance, you could actually get a return on investment under commercial financial sort of investment requirements. But also, I think the message here was that the climate change impact is already large enough that you can't, this kind of adaptation was not enough to eliminate all of that anthropogenic risk, the climate risk at this stage. Okay, the second example brings together agricultural drought, food security, and insurance into one study. This is quite a different piece of work we did, but the question here was, has climate change increased, first of all, populations in Africa at risk from drought? And these are generally rural populations who are quite dependent on on-farm production, small farm production for their food security. And then related to that, has climate change altered the cost of the kind of catastrophe insurance that is increasingly being pushed in developing countries to cope with the recovery costs from drought and famine? So here we had a really nice collaboration with one of the big sovereign insurance entities, something called Africa Risk Capacity. So I don't know if any of you heard about the Caribbean Catastrophe Facility, but basically that was the first example of this, where the Caribbean states got together with support from international donors to create a catastrophe insurance facility that paid out for post-hurricane recovery costs, and it was an immediate payout if the intensity of the hurricane was above a certain threshold. So it's called index-based insurance, essentially. So you don't have to go and waste months and years doing assessments after the example. It's just an immediate payout. So Africa Risk Capacity is running similar scheme in Africa, but with, initially trialing it on drought and food security. So they have a catastrophe model that they use to estimate the risk of food insecurity, of drought, food insecurity in different countries. It starts with rainfall and evaporation input. It has a water balance model, and then that's tied to country-specific information on what a reduction in soil water availability means for crop productivity. And all of the parameters in those models are actually locally determined with local agricultural experts. So it's quite a nice model in the sense that the local experts who know the local agricultural systems are involved in setting up the local parameters. And in addition to that, then they have population information. So you know if there's a shortage of, say, maize as a staple crop in a certain district, you can say how many people are at risk from the population information. And all of that comes through to an estimate of the population at risk on a district-by-district basis in a country, and that's aggregated up to a national level of a population at risk. And so, as with most catastrophe models, you model historic droughts, and you kind of work out a probability distribution for, in any one year, what's the likelihood of a certain number of people being food insecure. And from there, you do your underwriting of the cost of a given level of insurance. So what we were doing then was working with ARC to say, well, if we take an attribution-based approach and we compare the drought risk, population at risk in the real world today to a world without climate change, how would that affect both the number of people at risk, but also what the cost of insurance would be if you were underwriting it? And to cut a long story short, we worked in 4 of the countries that have frequently taken out sovereign risk insurance with African risk capacity, and looked at this kind of attributable influence of climate change on the severity of both food security and and the cost of insurance. So the blue graphs, the blue little bars here, are similar to that drought graph that I showed, where we've got essentially something that's equivalent to that risk ratio, but it's the fraction attributable human influence on people at risk or the cost of insurance. So if we look at Malawi at the top there, we're saying that about 40% of the people at risk expected to be at risk in any particular year, that's due to human influence on climate. So it's essentially increased the number of people at risk by quite a large amount. And then the really frightening one is the cost of insurance based on the underwriting mechanism. 65% of the cost of insurance today, index-based insurance today, is due to human influence on climate. So that really raises interesting questions about sort of what's fair and equitable in terms of insurance as a mechanism for coping with residual risks in climate change. Because the way this works at the moment, the government of Malawi has to buy that insurance. But you could argue that actually they should only be paying for 35% of the cost of that insurance, because they're not the ones who've increased that cost of insurance by 65%. So you can start to think about how you might use global finance mechanisms to make catastrophe insurance more affordable through using mechanisms, through getting some kind of understanding of where the cost can be attributed between kind of natural variability and the enhanced risk due to climate change. And there are actually mechanisms that are already kind of doing this. So the World Food Programme in Mauritania, one of these countries, actually not for climate change reasons, but just to expand the amount of insurance that's available, they actually come in as equal funding partners to the government of Mauritania. So if the government of Mauritania agrees to buy insurance for $10 million, the World Food Programme will come in with $10 million to match that, so that they double the coverage, essentially. Because anybody who works in food security will know that early action is a hell of a lot more cost effective than late action in terms of dealing with the impacts of the household impacts of food security. Yeah, so I will stop there. Just some implications from this work. I think taking this attribution sort of framework and applying it in terms of impacts modeling or looking at impacts really does allow you to come up with some methods of quantifying both the human influence on the impact, but perhaps more importantly, if you bring in the adaptation component, you can start to disentangle how effective adaptation is in a similar kind of framework. And that's one of the big challenges in the adaptation space at the moment, is actually coming up with robust estimates of how effective adaptation is in terms of, or potentially it is, because there just doesn't seem to be the modeling framework to do this. This is one way to do it, provided you have models that you feel are robust enough to be able to do this. I wouldn't use the exact figures in anger for any investment decision, but I think it gives you ballpark figures about the quantum of effectiveness that you might be able to realize. And one of the challenges we have in adaptation investment, if you're following international climate finance debates, it's very clear that only about 10% of the total climate finance costs are going to come from international grant mechanisms. The rest has to come through private sector investment. But the private sector is not investing in adaptation because they can't see ways to get a return on the investment. So these kind of approaches can maybe help demonstrate what that return on investment might be. There's an interesting feed-through into debates on losses and damage, and loss and damage, which is a hot topic at the moment within the UNFCCC. I doubt that we'll ever be able to use these mechanisms to actually quantify what a loss and damage fund should be paying for a particular event, because that's too hot a topic. But doing this kind of work, I think, can demonstrate the magnitude of the investment that might be needed collectively. If you have a number of case studies that are looking at impacts, rather than saying you need to pay X for this study, you can get a sense of the magnitude of the investment that might be needed in a loss and damage fund. Yeah, I'd say that one of the challenges is that it's much harder to work in the impact space than in the weather and climate space, because each, we use global climate models. You run them once, you can extract data from them for many different locations. If you're getting into impacts, you really need models that can capture the local context. So it becomes a more complicated task to do this. But my dream is to kind of set up some kind of operational impacts attribution platform where, at least for some common perils and hazards, we can be in a situation where we can actually go further than just looking at the extreme event and get into what that means on the ground. For instance, like we've done with agricultural drought, food security, water resources, flooding, and maybe even using econometric models, looking at economic impacts of some of these events. So that's it. I just want to acknowledge a huge bunch of people that I work with on various different aspects. So these are all co-authors and collaborators, or students, or people who take on admin jobs, which means I can do more research. But yeah, it's been a great team to work with, and I'll stop there. Thanks very much.
Thank you very much, Mark, for a very inspiring talk. I think we have some time for questions, and I think there are mics, actually. I see Jason has handheld mics. So, floor is open for questions. While everybody is thinking, Mark, how are you actually looking at that new introduction of another fund, in essence, for loss and damage when we are still struggling with the adaptation fund? So are they starting to compete with each other, and how is that really, in your view, playing out?
It's still very complex, because the way that loss and damage is defined under the Santiago kind of agreement or network sort of framing is, I can't remember the exact terms, but there's kind of there's the adaptation side of it. So adaptation is kind of embedded in that framing, which is kind of around reduction and avoidance. And then the third arm of loss and damage is recovery. And so there's a big blurring between what the adaptation fund, because loss and damage by definition is the residual impacts that you can't avoid through adaptation, whether that's hard limits to adaptation, like, okay, you're on an ocean atoll and sea level rises, you have to migrate, or soft limits, which might be more socioeconomic, cultural, other limits to adaptation. So there's a gray area in the middle there, and I don't think anybody's figured it out at this stage. And that's a general problem, I think, with climate finance generally. So the whole separation of climate finance from development finance as two separate pots of money means that we really want to be financing development in an integrated way that takes climate risk into account. You're creating these separate games where people are having to chase the money in ways that actually doesn't make sense, really. So I think the loss and damage fund is going to create similar problems, but at least there's a bit of learning from the adaptation fund and the green climate fund, that if people are clever, they might be able to do something better this time around. Yeah.
Okay, we have a question up here.
Thanks, Mark, for sharing your impressive body of work. So my question is, I was wondering, from your models, can you be able to separate, how do you treat scale, if you can be able to separate human impact, for instance, in South Africa versus human impact from out of South Africa? How do you separate that in your modeling?
Can you just explain a bit more what you mean? Sorry.
For instance, a lot of your work is interested in the impact of human on climate change.
Yeah.
And so I'm wondering, how do you separate, in terms of scale, the impact maybe on a local level, on a national level, or even international level?
Yeah, okay. So when you get into the kind of some of the economic side of things, you can, I mean, there are different ways of doing it, but people have tried to, I think there was a recent study of, I think it was the heat wave in China, where they tried to sort of do maybe it's a different way around, but actually take that Chinese impact back into what it means in terms of every person in every country's contribution to that impact. So it's basically taking that attribution back and then saying, okay, you guys in the US, you've emitted a lot, so what does that mean in terms of your individual responsibility for your collective history of emissions in terms of that particular impact? Yeah, I don't know if that's what you're talking about, but if you're looking at what the impact means per individual, that depends on how you model it, right? So if you think of the drought risk modeling, you can get down to a district scale because we know what, so we can kind of match a little bit sort of what's happening at a district scale to the human influence. But if you went down to a household scale, I think you'd be getting a little bit too disaggregated, and there'd be too many weak links in the chain to be able to say anything that would stand up in a court of law or in a scientific paper. Yeah. I don't know if I've answered your question, but that's, yeah.
Just very quickly following up on, just what you said here, what stands up where, let's say court of law. Where do you think the attribution work is with respect to being able to actually make a case that could actually, let's say, be used in a lawsuit against somebody?
So it depends on the type of lawsuit, right? So if it's a criminal lawsuit and you're talking beyond reasonable doubt, then it's quite challenging, right? Because I mean, you can imagine you're in a courtroom and you show one of my nice graphs that shows that it's like the risk ratio for that particular impact is greater than 1 at a 99% confidence interval. That sounds like beyond reasonable doubt to me. But then you'll have the defense lawyer wheeling in somebody who starts to unpick, in the typical way that climate skeptics do, some of the problems or challenges in climate modeling, and then you start to create reasonable doubt. So I don't know if it's possible if we're in that stage yet, but if you're in more of a civil kind of environment where it's the balance of probabilities, then I think actually some of this evidence coming out is actually starting to show that you could probably convince a jury or a judge that the balance of probabilities weigh on the side of climate change.
Because we do actually see some legal action coming into the action space of moving some of the climate issues along. There was a question over here. Is the mic on?
Do you want to shout?
Yeah,
okay.
I think it's on now.
Yeah, now it's on.
Thanks, Mark. That was really very insightful. So, so my question is that climate is obviously the climate sort of scenarios. They're dynamic, and the change is dynamic, and people are responding to them as we talking. I mean, and in the form of adaptation. Are there models that also look at feedback of these adaptation into the system, like how adaptation may actually be accelerating some of what biophysical changes that we are seeing?
Yeah, so there are people who do that kind of modeling, and it happens at a range of different scales. So there's a whole industry, cottage industry around agent-based modeling, which would try to model sort of whether it's a household or a community, and provided you sort of know what some of the sort of decision preferences are through doing good, solid social science work, you can start to model those individual agents, and sometimes you see really interesting emergent behavior coming out of at least of the model. And then right at the other end of the scale, we have what are called integrated assessment models, which are essentially global, sort of a rather poor sometimes merging of global general equilibrium economic models with impacts models that try to simulate some of these feedbacks, but those are at very large scale, at the regional scale. And there hasn't really been a lot done, I think, at those intermediate scales. So some people are trying to model at the national scale, but I'm really skeptical of those sort of GEC type models. They just, they don't capture the real world very well, and they tend to optimize for profit or economic efficiency rather than the kinds of things that actually make people adapt in the real world. So I think there's a big, if we think that it's important to do it, and I'm not sure that it is, but there's a big gap in actually modeling those kind of things and understanding those feedbacks. But one of the interesting things that came out of the last IPCC report was, I don't know if people who are aware of this kind of the IPCC climate risk propeller, they call it, but it's like this big propeller with 3 arms to it, and one of them is around the hazard, one of them is around vulnerability, and one of them is around adaptive capacity, and risk, which is like the way IPCC defines it, the likelihood of a negative outcome is a function of the interaction of all of those. But we did some work together to actually bring in a 4th propeller, which is around responses. So responses can actually change risk as well, either in a positive or a negative way. So, there's a lot of literature around maladaptation, right? Or adapting in the water sector, and then actually having, so one example from Kenya, for instance, is local water harvesting increases water availability, but increases malaria risk, right, at the same time, because you're creating standing water for it. So I think some of those things, people are talking about them, but it's a really important area to get a handle on, and why integrated thinking from an adaptation perspective is really important. Otherwise you miss out on some of these sort of trade-offs or unintended consequences.
And mentioning IPCC and adaptation, one of the major outcomes of that report was pointing towards the limit of adaptation, that we cannot rely on adaptation to make up for everything that we are lacking on the mitigation side. There was a question over here. Is it switched on? It doesn't seem.
Hello.
Oh,
Okay.
now there we go.
I'm an economist. I work on adaptation, but also how safety nets can be used to facilitate adaptation. And one of the things I'm wondering is, if we sort of focus on what's human-induced, to what extent will that drive us to scale down foreign aid and sort of foster assistance to adapt?
Why would you say that?
I'm just wondering if sort of now if people say, oh, well, we only contribute 20% to, say, the increase in frequency, maybe I should scale down. I'm already offering too much funds, and I might need to scale down. Or I should scale down because I'm only responsible for X.
Yeah, it depends on, I guess, your philosophical standpoint, right? So, and it gets a bit back to the question of, are we talking about development funding generally, or the climate component of that? And what maybe I'm being naive, but I think it's quite nice to illustrate that it's dangerous and perhaps creates a very confusing development funding environment if you don't start to tease out the different dimensions of, I guess, climate, of what you need to do to fund what I might call climate resilient development. So I don't know, maybe I'm being naive, but and maybe it's better to separate out these different things, but I think it's better to be transparent. Yeah.
Jose?
This work? Thank you, Mark. I'm going to ask you a question, asking you to put this research in the context of policy discussions in South Africa. So just this past Tuesday, your Minister of Natural Resources, Mantashe, gave a speech in Cape Town where he basically dismissed decarbonization in South Africa. He basically said that for the foreseeable future, South Africa is going to use a lot of coal, and if it has a chance, it's going to use oil if it's found.
Yeah.
It's quite a striking speech. I understand it's a political speech, but it's nevertheless striking because it's a very open statement that we are not going to decarbonize. Deal with it. What would you, if you had a chance to talk with him, and maybe you do every so often, how would you try to convey to him the implications of this work to that very fateful decision of we are not going to draw down on the use of coal?
I mean, yeah. So you have to unpick a little bit. I mean, there is a bit of an argument that so this is a whole different area that is kind of interest of mine, but I haven't got into a lot of detail, but is around climate finance to leave fossil fuels in the ground in developing countries, right? Because the argument, I guess, would be, it's not so much the case for South Africa, because, I mean, we are kind of one of the biggest historical emitters. So I can't remember what it is, but we're significant in terms of cumulative emissions. But so why should Mozambique not exploit its natural gas assets and, assuming Mozambique is well governed, get the benefit, the income benefit to enable them to kickstart the economy in the same way that the Emirates have done, right? So, and I think there's a few papers that have come out about this, about how you might finance keeping fossil fuel in the ground, because it's not the total value of the fossil fuels, but it's kind of around the revenue that the state would get out of those that could be used for development aid. So I think that's an interesting general question for developing countries, and it's really sad that when Ecuador, whatever it was 10 years ago, put forward this proposal for them to leave their oil in the ground, that nobody came forward and agreed to fund it, because that would have been a really interesting pilot. In South Africa, I mean, you know as much as me about the political economy of South Africa and the question of a just transition, and the fact that many of our Minister for Mineral and Energy Resources supporters are sitting in the mining and coal industry, right? So, whether it's, I would argue that it's actually a political thing rather than anything to do with economic development. But I would say to him, you could use this threat to actually bring in much more money for a rapid transition, so external investment. And if South Africa got its act together and could actually even, with the current just transition funding that they got potentially awarded at Glasgow, it's taken them 2 years to figure out how that's going to work. If they were actually at all competent, they would have had that running and being asked for more, so that there would be no penalty in moving rapidly out of coal.
If Gary?
Yes, thank you for a very interesting lecture. Have you talked with the insurance industry about any of this? And if so, what is their reaction? And the reason I'm asking the question is you seem to have disentangled things enough that they could make some pretty good guesses when certain parts of the world are going to be uninsurable.
Yep.
And to the extent that they think that they can do that, they're already making plans for not insuring chunks of the world.
Yep. Yeah, so I have had conversations in South Africa with the insurance industry there. Their big long-term fear is that they actually go out of business because everything becomes uninsurable. So for them, it's a bit of a longer-term existential challenge. If a lot of their perils are climate-related perils, as they call them, and so I think where a lot of them are moving is getting much more into the risk reduction side of things. So, for instance, one of our big insurers in South Africa does a lot of agricultural insurance, is actually providing financial support to municipalities for their disaster risk reduction and their fire management team. So they're actually paying for additional staff in fire management because that actually reduces their exposure to large-scale runaway fires. So they're seeing, I think the more innovative ones are seeing kind of working on the risk reduction side as being part of their new business model. And for instance, AXA Insurance, which is the biggest insurer in the world, has a whole new division, which is actually almost like a consultancy, which is around providing advice on risk reduction. So they're actually seeing it as a business opportunity as well at the same time. I mean, I think, I don't know enough about the details, but I understand right now in California, there's certain places that are uninsurable, or at least there's certain perils that you can't get insured for. And but I don't know whether in that environment, rather than the state becoming the insurer of last resort, whether public-private partnerships aren't a way forward to kind of share that risk rather than it just totally being transferred to state or federal sources. Which, I mean, that's, you know, the state is the insurer of last resort, right? Already in today's world. But, yeah.
Okay, so I think that's, I don't see any further questions. So let's thank Mark again.
Thank you.
And move to the atrium of the building for a little reception.
Okay, thank you.
Thank you all.